Once a beacon of light and life, a star begins its final act. A journey into darkness that will rewrite the fabric of the universe itself. Born from clouds of interstellar dust and nurtured by the fiery heart of nuclear fusion, it has burned for eons, illuminating distant worlds. But now, as its fuel wanes, gravity takes the lead, pulling it into an unstoppable collapse. The star contracts, its immense core folding under its own weight. Here, reality bends, and the laws of physics begin to falter. No force can withstand a certain colossal mass's gravitational crush of stars. What remains is not merely an object, but an enigma, an awe-inspiring black hole, a region where light is imprisoned, and time and space twist into unimaginable forms. This is no ordinary demise. It is a gateway to the unknown, a spectacle that leaves us in awe. In its final moments, the star's collapse reveals the delicate balance of the cosmos. Event horizons emerge like veils, cloaking singularities, those infinitesimal points of infinite density. Yet some stars defy the shadow of concealment. These naked singularities, unshrouded by event horizons, are singularities that are not hidden by an event horizon, and they tease us with glimpses into the universe's raw mechanics, exposing truths that challenge everything we know about time, matter, and existence. These collapsing stars whisper their mysteries as humanity peers deeper into the heavens. Each is a captivating storyteller, recounting the tale of creation and destruction, of forces so immense they forge the fabric of space-time itself. The ultimate destiny of these celestial titans, be it a black hole or a naked singularity, remains one of the most tantalizing riddles of modern astrophysics, a cosmic dance that continues to captivate and confound. The life cycle of a low-mass star must differ from that of a high-mass star. Upon depleting their internal nuclear fuel, stars such as the Sun stabilize into diminutive entities approximately 1,000 kilometers in diameter, known as white dwarfs. Nonetheless, a star with a mass greater than 1.4 solar masses cannot attain this phase, prompting Chandrasekhar to propose alternative scenarios. For decades, the ultimate destiny of a massive star has remained unresolved. Significant research has concentrated on this issue in recent years, rendering it one of the most critical unresolved problems in astrophysics and cosmology today. When massive stars exhaust their internal nuclear fuel, they experience a persistent gravitational collapse, resulting in a catastrophic reduction in the star's size due to gravitational forces. The general theory of relativity forecasts intriguing results for the collapsing star. These possess significant ramifications for fundamental physics and cosmology. We intend to examine these advancements here. In 1939, Robert Oppenheimer and Herbert Snyder initially developed a model of continuous collapse for a massive star utilizing the general theory of relativity, succeeded by SDAT in 1938, OSD. Although the terms black hole and event horizon were not coined until the 1960s, this calculation established their foundational concepts. We will examine these advancements and investigate how they facilitated various themes in black hole physics during the late 1960s and early 1970s, ultimately establishing the groundwork for several important astrophysical applications of black holes in modern relativistic physics. The notion of a black hole is neither novel nor inherent. For instance, contemplate a star and its particles or projectiles. Gravity posits that a star's mass correlates with the strength of its gravitational pull, necessitating a greater velocity for an object to escape its influence. Nevertheless, light represents the ultimate velocity attainable by any particle. Consequently, we can categorize objects as massive or compact, with their escape velocity exceeding light's. In that situation, no material particle or light rays can escape from the surface of a body, known as a black hole. Pierre-Simon Laplace indeed referenced this possibility in 1799. It is accurate to assert that, akin to human beings, stars possess a distinct life cycle. They originate in vast clouds of dust and intergalactic matter within the remote expanses of space and time in the distant areas of the universe. Upon their emergence, they undergo evolution and radiate brilliance for millions of years, ultimately progressing into a phase of dissolution and eventual extinction. Most of a star's luminous existence involves hydrogen fusion into helium and subsequently into heavier elements. Ultimately, the transformation of all the star's matter into iron terminates nuclear processes and prevents the generation of new internal energy. At this juncture, the omnipresent force of gravity governs the star's ultimate evolution. In the star's early stages, gravity attracted its matter towards the core, while the external pressures produced by internal fusion processes achieved equilibrium. This equilibrium ensures the star's stability, allowing it to sustain a typical existence of luminosity and the emission of light and energy generated internally. Upon the alleviation of internal pressures, gravitational forces dominate, resulting in the star's contraction and collapse. It is now established that for a star with a mass similar to or slightly greater than that of the Sun, the white dwarf phase represents a preliminary stage in the star's ultimate demise. A star with a mass exceeding approximately 1.4 solar masses cannot transition into a white dwarf's final state. Stars with a mass ranging from 3 to 5 solar masses will stabilize into a configuration referred to as a neutron star. Gravity forecasts an ongoing and complete collapse for increasingly massive stars. What will be its ultimate destiny? This is a highly compelling inquiry in contemporary astrophysics and cosmology, possessing significant implications for fundamental physics. Stars originate in vast, distant clouds of interstellar dust, primarily when shock waves, potentially produced by a supernova explosion, compress the matter. Gravity subsequently dominates, causing the cloud to contract further, while its central temperatures increase. Nuclear fusion commences in the core at a specific phase of the process. This marks the inception of a star, wherein the internal pressures created by the emitted heat and light counteract any additional gravitational contraction. In this scenario, the internal pressures and the gravitational pull achieve a stable equilibrium. Stars are perpetually generated in star-forming regions of the universe where conditions are conducive to these processes, as observed in the infrared light spectrum. These newly formed stars can generally possess mass equivalent to that of our Sun, a typical star, or even exceed it. Stars primarily consume their internal hydrogen, converting it into helium atoms and emitting energy. Heavier elements, including carbon and oxygen, are produced during this process, which ceases or diminishes when a significant portion of the matter is transformed into iron. Subsequently, the star cools, and the internal pressures diminish. Once more, gravity, an omnipresent force, dominates and compresses the star inward. Upon depleting its internal fuel, the Sun's core will contract due to gravitational forces, yet it will be sustained by a novel quantum pressure generated by rapidly moving electrons, known as electron degeneracy pressure. This object is identified as a white dwarf with a roughly 1,000 kilometers radius. Likewise, stars with masses exceeding that of the Sun will ultimately evolve into neutron stars, as previously indicated. The star will attain this state after an initial collapse, shedding a portion of its original mass. These entities consist solely of neutrons, formed during the gravitational collapse of atoms under the influence of a strong force. The quantum pressure of these neutrons sustains and equilibrates the star, which measures merely 10 to 15 kilometers in diameter. The ultimate result of collapse is contingent upon the star's initial mass, which stabilizes at a significantly reduced radius due to the counteracting pressures produced by either electrons or neutrons within. The concluding phase of a star's collapse generates a supernova explosion that ejects the star's outer layers. Nevertheless, stars exceeding the neutron star mass limit cannot transition into a white dwarf or neutron star state. The internal quantum pressures from the electrons or neutrons within the star are inadequate to counterbalance the collapsing star, as the gravitational force is significantly stronger. Consequently, an ongoing gravitational collapse occurs, which no recognized physical force can impede. The complete collapse becomes unavoidable once the star depletes its internal nuclear fuel. The life history of a massive star significantly contrasts with that of low-mass stars. A star with a mass 10 to 20 times that of the Sun combusts at a considerably accelerated rate, resulting in a lifespan of merely a few million years, while a smaller star, such as the Sun, possesses a lifespan spanning several billion years. What is the ultimate destiny of such a colossal star? This represents a significant unresolved issue in contemporary astrophysics and cosmology. Chandrasekhar and Lev Landau independently emphasized a crucial inquiry regarding the destiny of massive stars. They revealed that the evolutionary trajectory of a low-mass star fundamentally differs from that of a high-mass star. For a small-mass star, the natural white dwarf phase represents a preliminary stage in its eventual demise. Nevertheless, a star exceeding a specific critical threshold cannot transition into the equilibrium phase, characteristic of white dwarfs or neutron stars. We must subsequently conjecture alternative possibilities. The inquiry above illustrates the foundations of contemporary black hole physics. Following Chandrasekhar's initial discourse, the question of the final state of massive stars remained unresolved and elusive for an extended period. Although his research identified the stable configuration limit for white dwarf formation, the ultimate fate of significantly larger stars remains uncertain, as these stars cannot stabilize as white dwarfs or neutron stars. The matter is evidently significant in both high-energy astrophysics and cosmology. Observations of supernovae resulting from collapsing stars are closely linked to our comprehension of dark energy's existence in the universe and the cosmic acceleration it engenders. The observational evidence of distant supernovae indicates the universe's potential acceleration and the rate of this acceleration. A supernova is centered around the catastrophic gravitational collapse of a massive star, which produces a formidable shockwave that ejects the star's outer layers. If a star expels sufficient matter during an explosion, it may condense into a neutron star. Nonetheless, if matter accumulates onto the neutron star, a persistent collapse will ensue, necessitating further investigation. Conversely, stars that are considerably more massive than the typical supernova mass threshold undergo a continuous collapse at the conclusion of their life cycle, bypassing any intermediate neutron star phase. The general theory of relativity dictates the ultimate destiny of such a star. The standard laws of physics and quantum theory elucidate the formation of white dwarfs and neutron stars through electron and neutron degeneracy pressure, respectively. However, such quantum pressures can only counteract a star's gravitational collapse when its mass exceeds 5 to 8 solar masses. When the initial mass exceeds this threshold, these pressures can no longer sustain equilibrium within the star, resulting in its collapse under the full force of gravity, which compresses it entirely. The general theory of relativity now dictates the star's ultimate destiny, rendering the other three fundamental forces of nature inconsequential. The crucial point is that stars with masses several times that of the Sun are significantly more rapid and exhibit greater luminosity. Such stars cannot survive beyond 10 to 20 million years, a significantly shorter lifespan than our Sun, which will persist considerably longer. Consequently, the ultimate destiny of these ephemeral massive stars is pivotal to astronomy and astrophysics. We must investigate the final outcome when a massive star depletes its internal nuclear fuel. The general theory of relativity posits that a collapsing massive star culminates in a space-time singularity characterized by infinite matter, energy densities, space-time curvatures, and other physical quantities. Consequently, it is essential to ascertain whether the super-ultra-dense regions created during stellar collapse are observable by an external observer or concealed within a black hole and the gravitational event horizon that may arise during the star's collapse. This is a critical unresolved issue in contemporary black hole physics. To comprehend the ultimate collapse of a massive star, it is essential to analyze the system's temporal evolution and dynamical development through Einstein's gravitational equations. The star contracts under the influence of its own gravity, which ultimately prevails over other fundamental interactions of nature, including the weak and strong nuclear forces that usually generate the outward pressure necessary to counterbalance gravitational attraction. In the late 1930s, Oppenheimer, Snyder, and Datt employed Einstein's theory to comprehend the ultimate destiny of massive collapsing stars. OSD examined the ongoing gravitational collapse of a pressureless, homogeneous, uniform density matter cloud through the lens of general relativity. The most fascinating result indicated that the collapse, as it advances over time, forms an event horizon. The collapse creates a unidirectional surface in space-time, making a specific space and time imperceptible and inaccessible to remote observers in the universe. John Wheeler introduced the terms black hole and event horizon in 1969. Consequently, we refer to this concealed region as a black hole. Therefore, the ongoing collapse of a substantial matter cloud in the OSD model results in a black hole, which is the final state of collapse. The OSD work employed numerous simplifying assumptions for the intricate Einstein equations. Oppenheimer, Snyder, and Datt assumed a strictly homogeneous density distribution within a star, indicating uniformity throughout. Furthermore, they disregarded the gas pressure forces within a spherical star, considering them negligible and consequently assuming the matter consisted solely of pressureless dust. Their computations indicated that an event horizon surface forms as the collapse advances, preventing any material particles or photons from escaping the region within the horizon. Upon the star's collapse to a radius smaller than the event horizon, it has transitioned into the black hole region of space-time. It subsequently contracts to a singularity of immense density. For a collapsing star to form a black hole, an event horizon must emerge before creating the final singularity. The causal structure of space-time indicates that no material particles or light rays can escape from the region once the star crosses the event horizon, thereby isolating it from distant observers in the universe. The OSD model offers an internal perspective of the imploding cloud. This solution typically relies on the characteristics of matter, the equation of state, and the physical processes occurring within the stellar interior. Nevertheless, presuming the scenario involves pressureless dust with uniform density, it is feasible to resolve the issue explicitly and analytically. In the case of OSD, we presume the energy-momentum tensor of pressureless dust, solve Einstein's equations to ascertain the metric potentials, and derive the geometry of the collapsing dust sphere. To comprehend the formation of an event horizon and black hole during the collapse of a massive star, we must first recognize that the star ultimately collapses into a singularity characterized by infinite density and space-time curvature. The general relativity calculation indicates that the star's collapse amplifies the gravitational force at its surface, ultimately reaching a point where no light signal can escape. T-his is the era when an event horizon has emerged, and the star transitions into the space-time black hole domain. The infalling emitter experiences no notable sensations upon crossing the horizon, yet distant observers cease to perceive its emitted light. The star's intense gravitational force induces the formation of a unidirectional membrane known as the event horizon. The collapse persistently compresses the star within the horizon into a space-time singularity. The contemporary physics for elucidating the formation of black holes as the terminal phase of stellar collapse is predicated on the OSD dust model. In this scenario, all matter collapses into the space-time singularity concurrently, while the event horizon develops before the singularity, thereby completely obscuring it. This is the process by which the collapse forms a black hole region within space-time. We must investigate the ultimate outcome of a gravitational collapse within an appropriate gravitational theory, as the consequences of extreme gravity will be pivotal in this context. Consequently, The OSD model employs the general theory of relativity to analyze the ultimate destiny of an idealized massive matter cloud, as previously delineated. An event horizon was observed before the dynamical collapse that resulted in the space-time singularity. This led to the creation of a black hole in space-time. A black hole obscures the singularity, and its subsequent collapse results in the Schwarzschild geometry previously mentioned. It would be beneficial to examine and comprehend the fundamental characteristics of this gravitational collapse scenario in detail. The collapse commences from a standard configuration at the initial time, t0, for the collapsing spherical homogeneous dust cloud. The process becomes irreversible upon the onset of collapse, resulting in the star's continual contraction to increasingly diminutive diameters. Initially, and subsequently, when the star's surface is beyond the event horizon, or Schwarzschild radius, any emitted light ray can reach a distant observer. Once the star collapses beneath the event horizon radius, specifically at R2002 Mens, it enters the no-escape region in space-time, referred to as the black hole. The event horizon radius delineated this region, which evolves in space-time as the collapse advances. Subsequently, all matter collapses into a singularity of infinite density and curvature at the center, R0. This inevitably transpires in a finite proper time, as perceived by an observer on the star's surface. Consequently, the star undergoes collapse at a definitive future moment, compressing all its matter into the space-time singularity at its core. A singularity now exists at the center, with the remainder of space-time devoid of matter, its geometry characterized by the Schwarzschild metric. This is termed the Schwarzschild black hole. We designate any occurrence in this region of the Schwarzschild black hole as a trapped surface. This two-dimensional space sphere is characterized by the convergence of outgoing and incoming families of light rays emitted from this point. Consequently, neither light nor matter particles originate from this area. In the resultant Schwarzschild geometry, the black hole region spans from the center to the Schwarzschild surface, with the event horizon functioning as the outer boundary. At the event horizon, radial outward photons remain stationary, while all other photons are drawn toward the black hole's center. No information from this black hole can escape beyond the R2 Men boundary. Due to the inability of emissions or light rays from the singularity to reach an observer at infinity, it is causally isolated from the external spacetime. The spacetime area contained within the event horizon constitutes the black hole region. The dimensions of the event horizon are proportional to the total mass undergoing collapse. Specifically, an increase in stellar mass expands the event horizon. If the collapsing star has a mass of approximately 10 solar masses, the event horizon or black hole will measure about 60 kilometers in diameter. Any occurrence within the event horizon cannot transmit signals to distant observers. Conversely, occurrences beyond the horizon can communicate with distant observers. The OSD collapse model ultimately evolved into a fundamental paradigm for black holes. It is posited that all massive stars in the universe ultimately collapse into black holes after their life cycles, preserving their qualitative characteristics. In recent decades, substantial research and astrophysical applications concerning black holes have been developed, which is pivotal in contemporary astrophysics and cosmology. Such black holes could assimilate additional matter from their environment and increase in size progressively. Two significant characteristics emerge from the previously mentioned gravitational collapse scenario. Initially, an event horizon emerges as the collapse progresses, and subsequently, the singularity characterized by infinite density and curvature concludes the collapse. Both of these ultimately became the focus of extensive discussion and debate for many years, and have significantly influenced the subsequent evolution of gravitation theory, as we will examine here. Remarkably, this model garnered minimal attention following its development. During that period, gravitational theorists and astronomers considered it implausible for a star to attain an ultra-dense state in its evolutionary process. The distinctive characteristics of the OSD model and their extensive implications were already evident. Nevertheless, the dominant perspective largely disregarded these characteristics, contending that nature could never achieve such an extreme contraction of a physically plausible star. The collapsing cloud was believed to attain equilibrium before reaching a singularity. Einstein authored a paper in 1939 contending that a definitive state for a star is unattainable. Gravitational physics remained a relatively stagnant discipline until the introduction of general relativity in 1915, experiencing minimal advancements until approximately the 1950s. Nevertheless, the 1960s witnessed the emergence of novel observations in astrophysics, including quasars and extremely high-energy phenomena, such as energetic galactic jets. These observations and significant theoretical advancements, including examining the global structure of spacetimes and singularities, resulted in crucial findings in black hole physics, relativistic astrophysics, and cosmology. Consequently, identifying quasars and radio galaxies in the 1960s rekindled interest in black hole physics throughout the 1970s. No alternative physical processes can account for the extreme energies detected in quasars and energetic galactic jets, reviving interest in gravitational collapse models. The dynamic formation and physical characteristics of black holes and their surrounding spacetime regions are the subject of renewed interest. The gravitational collapse of massive stars and their eventual outcomes, along with black holes as possible physical mechanisms driving very high-energy phenomena in the universe, have once more garnered our interest. Consequently, event horizons and space-time singularities emerged as a topic of considerable discourse. Creating an event horizon is one of the most captivating aspects of OSD's examination of the collapse of a massive star. Physicists promptly acknowledged the distinctive characteristics of the OSD model, notwithstanding the limited prevalence of the terms event horizon and black hole during that period. This model for the ongoing collapse of a massive star possesses the notable physical characteristic that, as the collapse progresses to a specific stage, the star crosses the horizon. At this point, the causal structure of spacetime prevents any material particle or light ray from escaping the star's surface. As observed, another compelling characteristic is that once the star crosses the horizon, the physical radius of the entire star diminishes to a negligible value after a finite duration. All matter ultimately converges simultaneously to a singularity at the center. The primary contention regarding the OSD model was that researchers posited both the spacetime singularity and the event horizon emerged due to the model's excessive idealization. The existence of spacetime singularities was already known to researchers in the 1930s. Nonetheless, it was posited that the singularity present in the OSD model and other significant solutions to Einstein's equations, including the Schwarzschild and FRW models, would not manifest in more realistic solutions. Moreover, it was believed that a horizon or black hole could never form due to the impossibility of compressing a star to such diminutive dimensions. We will examine how the singularity theorems addressed the problem of singularities by illustrating their emergence in significantly broader contexts. The cosmic censorship conjecture posits that all realistic massive stars will collapse analogously to the OSD collapse, preserving identical qualitative characteristics. This indicated that massive stars would implode into a space-time singularity concealed within a black hole. For several decades following the advent of the general theory of relativity, the primary concerns in gravitational physics were space-time singularities and event horizons. We also examined the Schwarzschild and FRW solutions and the OSD gravitational collapse model, which originated in the early years following the development of the theory. Concerning space-time singularities, we have determined that singularities occur in general relativity across various scenarios and plausible physical conditions. Nevertheless, our present comprehension of singularities' nature, structure, and properties is constrained, as they can emerge in diverse scenarios within general relativity, whether in static or dynamically evolving models. The second significant issue pertains to the formation of event horizons and their concealment of singularities during gravitational collapse. In the OSD collapse scenario, we noted that the event horizon completely obscured the singularity within the zone of no communication with external observers, similar to a black hole. In the early 1970s, physicists resolved the question of singularity occurrence and posited that, similar to the OSD scenario, event horizons would obscure the singularities of collapse whenever they arise. In 1969, Penrose first introduced the assumption known as the cosmic censorship conjecture. Under typical physical conditions, gravitational collapse invariably forms a black hole in space-time, with the curvature singularity of the collapse concealed within it. In accordance with the censorship hypothesis, substantial progress has transpired in black hole physics, leading to the development of several essential theoretical components and astrophysical applications related to black holes. We subsequently examined black holes' classical and quantum characteristics and introduced intriguing thermodynamic analogies related to them. Subsequently, we formulated numerous astrophysical applications for black holes in the actual universe, including models that utilize black holes to elucidate phenomena such as jets emanating from galactic nuclei and highly energetic gamma-ray bursts. Researchers recognized that the homogeneous and pressureless dust collapse represents a highly idealized model. The OSD model operated under these assumptions due to the complexity of Einstein's equations and the inability to resolve the system. The nonlinearity and complexity of Einstein's equations, which dictate the dynamical evolution of stars, render the examination of realistic dynamical gravitational collapse models within Einstein's framework a formidable endeavor. Consequently, minimal advancement occurred in the decades following the OSD efforts. Physicists have consistently recognized the essential significance of examining more realistic models of the gravitational collapse of massive stars to attain a profound comprehension of black holes. The OSD scenario overlooks pressures that significantly influence the dynamics of any realistic star, and the density distribution cannot be homogeneous or uniform. Genuine stars generally exhibit greater density at their cores, which diminishes outward. They also possess non-zero gas pressures internally, and their forms are not perfectly spherical. Physicists had an immediate and pressing impetus to adopt censorship. In the early 1960s, observations of very high-energy phenomena in the universe, including quasars, radio galaxies, and active galactic nuclei, were inexplicable by any established physical mechanisms. Intense gravitational fields likely significantly influence these phenomena, requiring a comprehensive and meticulous application of general relativity for their elucidation. The censorship hypothesis significantly propelled advancements in black hole physics. Assuming it is valid, physicists examined the characteristics of black holes and formulated comprehensive laws governing black hole dynamics. They employed black holes to elucidate numerous ultra-high energy phenomena observed in the universe, including quasars and X-ray emitting binary star systems. By the early 1970s, physicists deemed it pragmatic to accept censorship and achieve substantial advancements in black hole physics. The focus was on examining black hole solutions to Einstein's equations, along with their various properties and applications, rather than on the challenging investigation of gravitational collapse. Researchers broadly defined black holes and meticulously examined their properties. These advancements garnered significant attention from researchers examining the implications for extremely high-energy cosmic phenomena. As previously discussed, the result of OSD gravitational collapse is a black hole. It comprises two components. At the singularity, space-time compresses and annihilates all the star's matter. A region of space encircling the singularity exists from which distant observers cannot escape. The boundary of this region is termed the event horizon. Once any object or light rays penetrate this region, they cannot escape. Upon the collapsing body reaching the horizon, no emitted light can escape, rendering it entirely confined within the horizon. The Schwarzschild geometry, established by him in 1916, signifies the definitive geometry of this black hole. The notion of an escape cone is instrumental in comprehending the genesis of a black hole during collapse. Examine the collapsing star and an observer situated on its surface, emitting light beams as the collapse advances. The light from the observer can escape and reach a remote observer as long as the star has not crossed the event horizon. Upon reaching the horizon, all emitted light rays converge upon the singularity at the center, except one radial ray that remains at a constant distance from the singularity at the horizon. Moreover, once the observer crosses the horizon, all emitted rays are drawn into the singularity, rendering escape impossible. Ultimately, the singularity consumes the observer, obliterating them from existence. The black hole possesses an exceedingly strong gravitational field. Consequently, the behavior of light rays and particle trajectories near a black hole is significantly important. A fascinating feature of these intense gravitational fields is the presence of a photon sphere surrounding the black hole. This is a surface where photons can theoretically traverse in a circular orbit without succumbing to a gravitational well. This surface possesses unstable light-ray orbits, which may either be captured by the black hole or escape with minimal disturbance. The photon sphere is crucial in gravitational lensing, which involves the deflection of light rays by a black hole. The OSD collapse is a specialized model, analogous to the Schwarzschild black hole. If the star consists of spherical dust with no pressure and is entirely homogeneous, its collapse will form a black hole. However, most stars are inhomogeneous, not perfectly spherical, and exhibit rotation. Consequently, their forms may deform as the collapse advances, and their rotational velocities increase. Understanding how these alterations influence the collapse and formation of black holes is essential. Acquiring fully resolved analytic models, such as the OSD, will be exceedingly challenging in this scenario, necessitating numerical models to analyze the collapse of the matter cloud. The Kerr metric represents a rotating, axisymmetric solution to Einstein's equations. The Schwarzschild geometry naturally arises from the OSD collapse. Nonetheless, we are unaware of any collapse model that could result in a Kerr geometry as the final collapse state. Nevertheless, the no-hair theorem posits that all collapsing configurations should generally culminate in the emergence of a Kerr black hole. A Schwarzschild black hole is defined solely by its mass, whereas a Kerr black hole is defined by its mass and angular momentum. Kerr black holes possess numerous astrophysical applications and fascinating characteristics. One is that they pull their surrounding spacetime in the same direction as their rotation. Roger Penrose demonstrates that this phenomenon could enable a spinning black hole to be an energy source. Recent computer simulations conducted by Ramesh Narayan and his collaborators demonstrated that by manipulating spacetime, an accreting black hole can expel a small portion of gas in the form of powerful, collimated, relativistic jets. Decades have elapsed since identifying such jets, inciting discourse regarding their energy source. A prevalent explanation is that the energy originates from the black hole itself. Computer simulations indicate that this possibility is probable. Observational evidence also supports this interpretation. During the 1970s, the pinnacle of black hole physics development, numerous analogies were established between the behavior of black holes and the conventional laws of thermodynamics. The concept that space-time is asymptotically predictable, akin to cosmic censorship, along with the distant Minkowski flat behavior of space-time, demonstrates that the area of an event horizon consistently expands and never contracts. This closely parallels the second law of thermodynamics. The area theorem by Hawking ensures the continuous increase of the surface area of any black hole, contingent upon the matter and fields interacting with it, adhering to the weak positive energy condition. Researchers have identified parallels between black hole behavior and the first and third laws of thermodynamics under different assumptions. These possibilities have generated considerable interest in black hole physics. The second law, the area theorem, does not universally apply in an asymptotically flat cosmological context. Subsequent to the advancements in black hole thermodynamics outlined, researchers investigated semi-classical gravity within curved spacetime, such as that surrounding black holes. The most notable outcome was the Hawking radiation phenomenon, inferred by Stephen Hawking in 1975. The event horizon induces a rapid and faint radiation emission, resulting in the black hole's evaporation. Ultimately, the complete black hole will undergo evaporation. Nonetheless, this phenomenon is exceptionally gradual and not readily detectable in typical black holes, with masses of several solar masses. This outcome has underscored the intriguing potential of quantum gravity. By definition, a black hole does not emit light, rendering direct observation unfeasible. Therefore, a direct confirmation of a black hole's existence is unattainable. Consequently, no light emitted from its surface, the event horizon, can escape to reach a distant observer. The black hole possesses an extraordinarily powerful gravitational field that influences its environment with observable consequences. In actual astrophysical scenarios, matter surrounding a black hole will be drawn into it. As the descending material from the accretion disk encircling a black hole nears the black hole's surface or event horizon, it accelerates and increases in temperature. This intensely heated matter will emit strong X-rays, a characteristic indicator of a black hole's presence in the universe. Many contemporary X-ray telescopes utilize this phenomenon to detect the X-ray emissions from the accretion disks encircling compact objects thought to be black holes. One notable candidate is the object Cygnus X1, which has been the subject of observation for an extended period. Applications in astrophysics. Black holes have been extensively utilized to model extremely high-energy astrophysical phenomena observed in the universe. These encompass potent jets released from galactic nuclei, quasars, gamma-ray bursts, and other phenomena. Previously, we noted that Kerr black holes may elucidate the phenomenon of galactic jets. No conventional forces can account for such extreme energy phenomena in the cosmos. Consequently, as inherent outcomes of general relativity, black holes present a relatively natural alternative in this context. The field is advancing swiftly, with numerous observational missions and sophisticated computer simulations emerging in recent years. What constitutes a naked singularity? It is essential to comprehend the concept of a visible naked singularity. We can ascertain whether event horizons invariably encompass singularities, or if they can exist independently of them. As previously stated, the matter, energy densities, space-time curvatures, and all relevant physical quantities escalate exponentially as one nears a space-time singularity. It is important to note that the singularity is not a component of space-time. All occurrences within the space-time continuum must adhere to regularity conditions, including well-defined gravitational potentials and the applicability of special relativity in sufficiently localized regions. Nevertheless, when contemplating a singularity within space-time, such a characterization is either unattainable or inaccurate. Consequently, it can be considered a boundary of the universe. Consequently, even beyond space-time, a singularity influences the entirety of universal physics. Indeed, the Big Bang functions as the origin of the universe. The Newtonian framework posits that the gravitational force between two entities, such as the Earth and the Sun, is computed as though their entire mass is concentrated at their respective centers. Should the Sun collapse into a black hole, it would condense all of its mass into a singularity, while both entities would continue to experience identical gravitational forces. Currently, analogous computations are conducted within the context of general relativity to determine, for instance, the gravitational radiation emitted by a system comprising a black hole and a star orbiting and ultimately accreting into it. With the entirety of the black hole's mass concentrated at its core. A space-time singularity is a region where general relativity ceases to function effectively. Indeed, we recognize that singularities within any theory signify its limitations and indicate its failure. Likewise, the presence of singularities in general relativity indicates areas of extreme density and curvature in the universe, where Einstein's theory of gravity fails. Although we acknowledge the essential existence of singularities, confirming their formation in gravitational dynamical processes under various physical conditions as predicted by general relativity, our understanding of their nature, structure, and properties remains limited. Notwithstanding the existence of space-time singularities, the theory does not explicitly associate them with the presence of event horizons. In principle, singularities may exist with or without horizons. In the absence of direct evidence, there is no definitive physical rationale to demonstrate that singularities must be concealed within event horizons and remain invisible. A naked singularity is a space-time singularity that can interact with distant observers in the universe, in contrast to the singularity concealed within a black hole, Figure 5.1. The latter is incapable of interacting with any event in space-time. The defining characteristic of a naked singularity is the existence of light rays and particle trajectories that originate from the singularity or its immediate vicinity and extend to distant observers in the universe in the future, Figure 5.1. This would facilitate the transmission of information from proximity to the singularity and ultra-dense areas to external observers. Families of non-space-like trajectories exist that extend infinitely into the future and converge at the singularity in the past. As we approach the singularity along these trajectories, the densities and space-time curvatures generally increase and diverge in the limit of proximity to the singularity. A singularity within a black hole cannot demonstrate such a phenomenon. In that scenario, information enters but never escapes the proximity of the singularity. Thus, to ascertain whether a specific gravitational collapse culminates in a black hole or a naked singularity, it is essential to evaluate whether families of future-directed, non-space-like particles or photon paths originate from the singularity or its immediate vicinity. Recent research on collapse identifies two categories of singularities: those enclosed by an event horizon within a black hole, and those that are not. The second category is referred to as a naked singularity. Consequently, both black holes and naked singularities may result from gravitational collapse under standard and plausible physical conditions. In contrast to a black hole, the naked singularity configuration possesses distinct theoretical and observational characteristics. The emergence of a naked singularity is defined by three principal attributes. 1. Initially, families of infinite light and particle trajectories originate from the singularity region, possessing a past endpoint at the singularity. 2. Secondly, a true curvature singularity exhibits densities and curvatures that approach infinity and intensify significantly as one approaches the singularity along these trajectories. 3. Ultimately, the comprehensive spacetime adheres to all physical regularity criteria, rendering it a compelling framework for examining physical phenomena in ultra-strong gravitational contexts. Prognostications of general relativity. Einstein's general theory of relativity posits that collapse must lead to the formation of a spacetime singularity, where physical parameters like energy density and spacetime curvature escalate to infinitely large values. The conventional laws of physics cease to function in proximity to a singularity. This is the domain of ultra-strong gravitational fields, where other fundamental forces of nature assume a subordinate role. In strong fields at ultra-small length scales near the singularity, quantum effects will become significant, and ultimately, a quantum theory of gravity will address the singularity. The singularity theorems in general relativity delineate the consequences of an ongoing collapse within a comprehensive framework of space-time, featuring a dynamic matter field. While the theorems indicate that singularities must arise under relatively broad conditions, they provide no insights into the nature, structure, or physical properties and implications of these singularities. Singularity theorems presuppose the following conditions. 1. The energy density of matter fields is positive. 2. A coherent causal framework is present within space-time. 3. The formation of trapped surfaces in space-time ensures the concentration of adequate mass within a sufficiently compact area. When these three conditions are met, the theorems indicate that the space-time must possess a singularity. Consequently, any general relativistic gravitational collapse originating from standard initial data in a space-time devoid of symmetry conditions, such as spherical symmetry, will result in a space-time singularity if the aforementioned physically plausible conditions are satisfied. The densities, curvatures, and other physical parameters will become infinite as we near this singularity. Consequently, any physically plausible gravitational collapse of a massive star at the conclusion of its life cycle must culminate in a space-time singularity. The previously discussed OSD collapse scenario represents a specific instance of general gravitational collapse, culminating instantaneously in a singularity, which is the ultimate end state of a collapsing matter cloud. As previously mentioned, singularity theorems solely predict the existence of space-time singularities, contingent upon a specific set of physically plausible conditions. They do not furnish information regarding the nature, structure, or properties of such singularities. They do not specify whether an event horizon will encompass such singularities, particularly those arising from gravitational collapse, or if they will be observable by external observers in the universe. The singularity theorems demonstrate that singularities must manifest as geodesic incompleteness within a space-time continuum. The theory of general relativity is unable to ascertain the sequence of occurrence between the event horizon and the singularity during stellar collapse. Consequently, a space-time singularity may still emerge during gravitational collapse without an event horizon obscuring it, thus creating a causal link with remote observers in the universe. In this scenario, ultra-high density and curvature regions can transmit signals to distant observers. Gravity forecasts intriguing results for the ultimate destiny of a massive collapsing star, with significant ramifications for fundamental physics. Consequently, it remains an unresolved question in Einstein's theory of gravity whether a robust curvature singularity resulting from a realistic collapse will be observable or concealed from a distant observer in the universe. The primary physical characteristic determining the visibility of a singularity is the interaction between the singularity structure and time curve and the formation of trapped surfaces in space-time. We can articulate it as follows. If S functions as a partial Cauchy surface, indicating a moment of simultaneity where collapse commences, then the future of S contains no naked singularities observable from future null infinity. This applies to the spherical homogeneous dust collapse, wherein the resultant space-time in the future is asymptotically predictable, and the censorship principle is upheld. Consequently, the failure of physical theory at the space-time singularity does not impede future predictions for the external asymptotically flat region. What would be the implications for other collapse scenarios if we permit inhomogeneities and non-sphericity? The presumption of censorship in an appropriate manner is essential for fundamental outcomes in black hole physics. The existence of black holes necessitates this hypothesis when one contemplates gravitational collapse in a general context. Naked singularities frequently arise in general relativistic gravitational collapse, if no constraints are placed on the structure of space-time or its energy momentum content. This is due to the fact that Einstein's equations relate the matter-energy composition of space-time to its geometry and curvatures. We can now select AB initio as space-time geometry featuring a naked singularity and subsequently substitute this into the left-hand side of Einstein's equations, considering the matter tensor as that quantity divided by 8p. Consequently, we inherently possess a space-time characterized by naked singularities. Nonetheless, this scenario does not ensure compliance with energy or regularity conditions, and it may be rather peculiar. Consequently, for censorship to be maintained, we must enforce several regularity and energy conditions on the matter. Developing a satisfactory and mathematically rigorous formulation of physical requirements poses a significant challenge for CCC. Creating an appropriate formulation would represent a significant progress in addressing the primary issue. In recent decades, significant advancements in gravity theory and relativistic astrophysics have occurred, particularly after the discovery of quasars in the 1960s and other high-energy phenomena such as gamma-ray bursts. In compact objects like neutron stars and scenarios with extreme energy densities and masses, strong gravitational fields dictated by general relativity are significant, and physicists have utilized these principles in other high-energy phenomena. Several models explaining gamma-ray bursts, which release the energy equivalent to the sun's entire lifetime in mere seconds, involve the collapse of a solitary massive star. The gravitational collapse of substantial matter clouds is the fundamental physical mechanism that generates a star from interstellar clouds, galaxies, galaxy clusters, and the universe. At this juncture, we recognize the necessity for a more comprehensive examination of gravitational collapse scenarios within the context of Einstein's gravitational theory, akin to the OSD research, yet generalizing and selecting more physically plausible cases and scenarios. The OSD model employs idealized and reductive assumptions to address Einstein's intricate system of equations. We aim to determine whether the ultimate outcome of gravitational collapse would result in a black hole or a naked singularity in physically plausible scenarios. This involved verifying the formation of trapped surfaces and event horizons during more realistic collapses, and determining whether this occurred prior to or subsequent to the emergence of the space-time singularity. This factor determines whether the space-time singularity resulting from collapse will be naked or obscured by the event horizon. Researchers examined various gravitational collapse scenarios involving distinct matter types, including the collapse of incoming radiation shells, the spherical collapse of pressureless matter, non-uniform dust, and perfect fluids with non-zero pressures. Researchers also examined instances of non-spherical collapse. We noted a consistent pattern in which naked singularities arise as the final result of the collapse. Moreover, in each instance, isolated trajectories and collections of non-spacelike geodesics emanate from the naked singularity, yielding a set of trajectories with non-zero measure. A naked singularity would emit a solitary front if solely an isolated null trajectory were to arise. The emission of a non-zero measure family of non-spacelike curves escalates the phenomenon to a more critical level. The resultant naked singularity demonstrated significant gravitational strength as the densities and curvatures diverged markedly as one approached it. Consequently, these characteristics were demonstrated to be authentic and irretrievable within the collapse's space-time. Consequently, our objective should be to examine how the incorporation of more physically realistic conditions and scenarios influences the ultimate state of collapse, specifically a black hole in the OSD dust collapse scenario. To expand the Oppenheimer-Snyder-Dat homogeneous dust collapse, we can examine the collapse of inhomogeneous dust and investigate the characteristics and configuration of the resultant singularity, with particular focus on censorship and the presence of black holes and naked singularities. This may elucidate the potential outcomes of gravitational collapse. The most straightforward physical generalization to consider is whether the result of a collapse would remain a black hole when accounting for inhomogeneities, such as increased density at the star's center. Should we revise the previous conclusions regarding homogeneous collapse to consider the inhomogeneities in matter distribution? Incorporating the effects of inhomogeneities is essential, as a realistic collapse often commences with inhomogeneous data displaying a centrally peaked density profile. We examined this issue comprehensively utilizing the Lemaitre-Tolman-Bondi models, which characterize the gravitational collapse of an inhomogeneous, spherically symmetric dust cloud. This represents an infinite-dimensional set of solutions to Einstein's equations, characterized by an inhomogeneous interior of the collapsing star and a vacuum exterior. The OSD model represents a specific instance within this category of solutions. To gain deeper understanding, the researchers initially examined a singular physical variable, specifically the incorporation of inhomogeneity in the initial density distribution of the collapsing dust cloud. This alleviates the rigid homogeneous density assumption of the OSD collapse model, enabling us to investigate the effects of more realistic inhomogeneous scenarios on the final state of collapse. In the subsequent chapter, we will examine the incorporation of additional physical characteristics, including non-zero pressures and non-sphericity, while contemplating the ultimate outcome of collapse. This study demonstrates that the introduction of inhomogeneities alters the understanding of gravitational collapse. We posit that in a collapse scenario, the density possesses compact support on an initial surface of constant time, allowing us to align the space-time at a boundary with the external Schwarzschild field, which contains a total mass m enclosed within the dust sphere. This framework allows for the examination of singularities. We can specifically reduce the problem of the singularity's nakedness to the existence of real, positive roots in an algebraic equation, which we derive from the fundamental quantities that define the collapse, such as the mass function and the velocity profiles of the matter cloud. The introduction of inhomogeneity in the star's initial density distribution can postpone the formation of trapped surfaces and the event horizon, resulting in a naked singularity as the final state of collapse. An inhomogeneous density profile is more realistic than the OSD model's assumption of a completely homogeneous cloud density, as stars demonstrate a higher density at their core that gradually diminishes radially outward. Taking into account the inhomogeneities in the initial density profile, we can illustrate a substantial alteration in the horizon's dynamics, possibly resulting in two separate outcomes from a typical dust collapse. These outcomes encompass the black hole, characterized by the horizon's formation preceding the singularity, and the naked singularity, in which the horizon forms subsequently. The latter scenario permits light rays to emanate from the central singularity, where density and curvature become infinite, to reach distant observers. Upon the escape of light rays, the material particles, or time-like geodesics, will similarly escape. Lemaitre-Tolman-Bondi models. Although dust models have received considerable focus in general relativity, Georges Lemaitre and Richard Tolman completely resolved Einstein's equations for the dust variant of matter, incorporating inhomogeneities, in the early 1930s. Their primary motivation at that time was the incorporation of inhomogeneities in cosmology. It is currently understood that, from a cosmological standpoint, the observed universe exhibits inhomogeneity up to scales of several hundred megaparsecs. Galaxies and superclusters, as inhomogeneities in the universe, are organized into walls and voids. Consequently, the universe's homogeneity, if attained, extends beyond this extensive scale. Consequently, examining an inhomogeneous solution to Einstein's equations for the universe is of significant importance. The general uniformity of the universe is an assumption referred to as the Copernican principle. A genuine consensus is required regarding the scale at which the universe exhibits homogeneity, partly due to the challenges in quantifying the dimensions of superclusters. The prevailing perspective posits that the universe can attain homogeneity on scales exceeding several tens of megaparsecs. Recent research indicates that we may need to re-evaluate extensive features of the universe to align with the standard model, incorporating dark energy as a cosmological constant. Certain researchers have adopted the more radical perspective that the universe tends toward homogeneity on scales as extensive as a gigaparsec. Subsequent observations will ascertain the veracity of this assertion. From this viewpoint, Andrzej Krasinski and others have employed the Lemaitre-Tolman-Bondi (LTB) models to represent an inhomogeneous universe in cosmology. Density inhomogeneities are evidently pertinent to the gravitational collapse of massive stars. In 1959, Hermann Bondi conducted a thorough analysis of inhomogeneous dust collapse. Consequently, individuals sometimes denote the general dust collapse models as the Lemaitre-Tolman-Bondi models. The study of gravitational collapse in dust has a long-standing history, originating with the Oppenheimer-Snyder-Dart models. Strict homogeneity is merely an ideal. We must account for density and homogeneities within a matter cloud. Following the introduction of the CCC in 1969, researchers investigated shell-crossing singularities in dust collapse models, identifying them as naked singularities. In 1973, Hans Seifert and colleagues from Germany proposed a model in which adjacent matter shells intersected, resulting in transient singularities not obscured by horizons. Nevertheless, these were dismissed as an observer would not be annihilated and compressed to a null volume while traversing such a phenomenon, which constitutes the authentic indication of a true singularity. The observer could traverse intact space-time to a different region. Realistic stars exhibit a higher density at their core, gradually diminishing towards the periphery. In 1979, Douglas Erdley and Larry Smarr conducted a numerical simulation of a model with zero pressure, followed by an exact mathematical analysis by Dimitrios Christodoulou in 1984. The model indicated a naked singularity at the center, where the physical radius of the cloud approaches zero. Richard P.A.C. Newman demonstrated that this singularity remains gravitationally weak, as the curvatures do not diverge with sufficient intensity in proximity to the singularity. Numerous researchers, including Newman and I in 1988, endeavored to establish a definitive theorem asserting that naked singularities are invariably weak, but their attempts were unsuccessful. I subsequently recognized that our understanding of gravitational collapse was insufficient to establish a universally applicable censorship theorem. We had to pursue the extended path of gradually enhancing our knowledge through the examination of case studies. Subsequently, researchers identified instances of non-uniform pressureless collapse, resulting in the formation of strong curvature naked singularities, or genuine crushing singularities, originating from standard initial conditions. Cale Lake and his associates, along with our team, formulated such collapse models. In 1993, Indresh Dwivedi and I presented an extensive general analysis of the inhomogeneous dust collapse scenario. Oppenheimer and Snyder examine a uniform pressureless collapse that culminates in the formation of a black hole. A more realistic density profile, characterized by increased density at the center and a diminishing density outward, may result in a naked singularity, a fascinating phenomenon. Nonetheless, these scenarios fail to consider the impact of gas pressure. What is the realism of a dust collapse scenario? The constraint of dust models lies in the presumption of negligible pressures, which may be significant during the final phases of collapse. Conversely, some contend that the dust equation of state could be pertinent during the final phases of collapse, suggesting that matter may exhibit characteristics akin to dust at elevated densities. This perspective was, for instance, proposed by R. Hagedorn in the 1960s and Roger Penrose. Moreover, in the absence of significant negative pressures, as suggested by the validity of the energy conditions, pressure may also exert a positive gravitational influence on the effects of dust, potentially leaving the conclusions unaltered. It is essential to evaluate collapse scenarios involving non-zero pressures and, if feasible, with appropriate equations of state. Pressures may significantly influence the final phases of collapse, necessitating an examination of the potential for pressure gradients to avert the formation of a naked singularity. We have analyzed the existence and termination of non-space-like geodesic families and the intensity of singularities during pressure-induced collapse. We can now present a comprehensive case study of a scenario involving a collapse that violates censorship, elucidating the progression of the collapse and offering a physical rationale for the absence of an event horizon. Permitting a higher density profile at the core of a collapsing dust cloud results in the emergence of a naked singularity instead of a black hole during the collapse. Let us examine this intriguing phenomenon and investigate the physics underlying the formation of naked singularities during collapse. We will examine the scenario illustrating the collapse of a dust cloud in the absence of gas pressure. The matter cloud initiates collapse from a state of rest, reflecting the phase in a massive star's life cycle when it has depleted its internal fuel and gravitational forces dominate. General relativity regulates this classical system, which adheres to all physical regularity criteria, including the positivity of energy density and the regularity of density and curvatures at the initial stage of collapse. If the density is presumed to be uniform at the outset, this would precisely correspond to the OSD model, with the collapse resulting in the formation of a black hole. We now examine a physically plausible scenario in which the star's density is greater at the core and diminishes as one progresses outward from the central region. To ascertain the collapse end state, it is essential to analyze the entrapment of light and matter as gravitational fields intensify. We can ultimately ascertain the equation of the confined region in spacetime, which delineates the dynamic evolution of the event horizon as the collapse advances. The crucial element in this context is the timing of the horizon during the collapse. If the horizon develops prior to the final singularity, a black hole is formed. However, if it is delayed during the collapse, observable, ultra-dense regions emerge in the universe. Significant inhomogeneity in the density distribution at the initial time postpones the horizon. If the density diminishes rapidly from the star's center, the result is a naked singularity. Conversely, a black hole emerges from a gradual decrease or a nearly uniform scenario. As the collapse advances, these intensify, and the focusing effect on light and matter amplifies. A moment arises when a region in space-time evolves, making light unattainable for any remote observer in the universe. The confinement of light simultaneously confines matter, as matter moves at a velocity inferior to that of light, maintaining its path within the cones. This pertains to the light rays originating from the star's surface, during a phase in which the star's radius has diminished to a distance proportional to its mass. As the collapse progresses, the density is exclusively a function of time, resulting in the eventual simultaneous compression of the entire cloud into a singularity in the future. the entrapment of light and matter transpires prior to the formation of the final singularity, leading to its total obscuration within the resultant black hole. No light signals or matter can escape from the ultra-dense regions adjacent to the singularity. The uniformity of matter density inhibits the simultaneous collapse of the entire cloud into the singularity. The various matter shells reach the singularity sequentially, with those at greater radii arriving subsequently. Consequently, light rays are never confined prior to the formation of a singularity, allowing them to escape from super-ultra-dense regions in close proximity to the space-time singularity. This absence of trapping occurs due to an insufficiency in the gravitational focusing effect on light and matter. Owing to the inhomogeneity and diminishing density of the star away from its core, there is insufficient total mass at any moment to induce complete light trapping prior to the formation of a singularity. Roy Martins, Naresh Dadich, and I examined the general relativistic phenomenon of delayed horizon formation and correlated it with the shearing effects induced by gravity in space-time. What are the physical implications and correspondences of such a phenomenon? Multiple interpretations exist, yet one plausible explanation may involve the formation of general relativistic shocks, resulting from inhomogeneity in these ultra-dense regions. These shocks may facilitate the escape and ejection of light and matter, even amidst exceedingly high matter densities. A naked singularity is defined by three primary characteristics. 1. Theories of an infinite number of light and particle trajectories arise from the singularity region. Secondly, it is. 2. The curvature singularity occurs as densities and curvatures approach infinity when approaching the singularity along these trajectories. Ultimately, the O-tema fulfills all physical regularity criteria, rendering this an intriguing context for examining genuine physical phenomena in regions of ultra-strong gravity. And a crucial assessment of the physical relevance of a naked singularity is its curvature intensity. A comprehensive classification and analysis of space-time singularities is accessible concerning their curvature intensity and physical importance. If at least one non-space-like trajectory approaches a singularity, and the space-time curvatures diverge rapidly as it nears the singularity, it is deemed to possess strong curvature. We have analyzed the potency of a naked singularity in various scenarios along non-space-like paths that converge at the naked singularity in the past, approaching the singularity's vicinity. It appears that we experience a pronounced curvature singularity, characterized by the rapid divergence of curvatures along all non-space-like geodesics that intersect the naked singularity in the past. This indicates that strong curvature naked singularities may occur in general relativistic gravitational collapse for various plausible equations of state. The scenarios examined are plausible as the energy conditions are fulfilled and the collapse progresses from clearly defined initial data. Any formulation of the cosmic censorship hypothesis must account for these scenarios, necessitating an examination of the structure of a naked singularity and the potential general constraints. Understanding the behavior of matter energy density and gravitational field strength during singularity collapse in standard models would be advantageous. This would provide insight into the authenticity and severity of such a singularity, in contrast to a gravitationally weak singularity, which lacks genuineness and may be extricable from space-time. Consider, for instance, the cosmological Big Bang singularity. In the Friedmann models, the radiation density escalates in proportion to the fourth power of the universe's scale factor, specifically 1s4, as the scale factor s approaches 0 at the singularity. Consequently, as s decreases, the radiation density becomes infinite. In this context, the scale factor will be T1 to 2, where T denotes the time elapsed since the Big Bang, and s equals 0 at T. 0. The equations of this cosmology indicate that the density diverges at a rate of 1t(2) as it nears the singularity. In the case of the Schwarzschild singularity, the density remains 0 across the entirety of space-time, as it represents a vacuum solution to Einstein's equations. However, we can graph the gravitational intensity in that scenario. Null geodesics, pertaining to photon trajectories that descend into the singularity, exhibit a gravitational strength that escalates and diverges at a rate of 1 ton K2, with Ka denoting the affine parameter along the geodesic paths, ultimately approaching 0 at the singularity. The Schwarzschild metric is a static solution that remains constant over time, whereas the Big Bang represents a dynamically evolving cosmological solution. In accordance with the prior discussion, we must investigate the density growth characteristics of a particular stellar collapse model as we approach the singularity. This aspect is especially significant for a naked singularity. If the density and space-time curvatures do not increase adequately during the approach, it may lead to a gravitationally weak singularity that could become decoupled from space-time. In examining this collapse scenario, we thoroughly comprehend the cloud's evolution and can compute the density escalation as we near the singularity. For clarity, we may regard the cloud's central line as a time-like geodesic in this context. The density evolution manifests as 1t2, with t forms H0 occurring at the singularity. Consequently, the density and curvatures increase significantly and become infinite as we near the naked singularity. Depending on the characteristics of inhomogeneity within the cloud, a black hole event horizon may either obscure the singularity or render it distinctly visible. In both scenarios, the aforementioned fact regarding the curvature growth as the singularity is approached remains constant. In the case of a black hole, it is essential to compute the density increase along the trajectories that enter the black hole and collide with the singularity at its core. Upon the formation of a naked singularity, families of non-space-like trajectories originate from it. We can trace these trajectories nearer to the singularity and compute the density increase as we near it. We can analyze families of photon or particle trajectories entering or exiting the singularity and investigate the curvature increase along these trajectories. We can compute the density increase or the curvature intensity as we near the singularity. The case under discussion exemplifies a naked singularity with pronounced curvature that is inextricably linked to space-time. The approach to the singularity reveals a significant divergence in density, affirming its authentic, strong curvature characteristics. The ultimate outcome of the gravitational collapse of massive stars and the concept of cosmic censorship has captivated researchers for decades, as it represents a significant discourse in black hole physics and its astrophysical implications, as well as in astrophysics and astronomy. Numerous unsuccessful endeavors have been made to articulate the CCC in various formats. Each of these endeavors has sought to elucidate, within various collapse models, the reasons for the non-occurrence of naked singularities, or, if they do arise, why they should be considered non-generic. If a naked singularity, instead of a black hole, emerges in gravitational collapse models that are more physically realistic than the OSD solution, a pertinent inquiry arises regarding the generic or typical nature of such a naked singularity outcome. Consequently, articulating genericity within gravitational theory is challenging, and no singular definition exists. This explains why scholars have explored various methodologies. A naked singularity cannot be deemed generic if the initial conditions leading to its formation during collapse are not generic. Specifically, the initial conditions that result in the naked singularity must constitute an open set of initial data. This implies that if a specific set of initial data produces a naked singularity, then all nearby initial data must similarly evolve into a naked singularity. A naked singularity is generally defined by a past incomplete null geodesic extending from future infinity. In the previously discussed LTB dust collapse scenario, we can address this matter utilizing the comprehensive framework that Indresh Dwivedi and I presented in 1993 for inhomogeneous dust collapses. We can articulate the fundamental depiction that arises and the overarching outcome we derive for this system as follows. The evolution of the general dust system and its eventual collapse are dictated by two parameters. The first is the mass function of the star, which delineates the total mass within a specified radius. The second parameter pertains to the velocities of the collapsing shells at the initial epoch. Energy conditions dictate that mass is invariably positive. The selection of shell velocities varies according to the physical system in question. For instance, the velocity function is suitably defined for a collapse from rest, representing the scenario of a star collapsing from an initial state of rest. We reach the following conclusion. Generally, for any selected initial density distribution, there exists a non-zero measure set of velocity functions that can lead the star to either a naked singularity or a black hole final state, contingent upon the chosen velocities. This selection is freely available and adheres to all regularity and physical plausibility criteria. This demonstrates the genericity and stability of the naked singularity within the context of a general dust collapse scenario. We will further investigate this characteristic later, emphasizing its relevance to other forms of matter. In the subsequent chapter, we will examine how the inclusion of pressures and other physical equations of state for general collapsing matter fields results in analogous features. In general, dust collapse models show black holes and naked singularities emerge naturally, and typically as the ultimate outcome of gravitational collapse. The introduction of increased density at the center inherently postpones the development of trapped surfaces, and the event horizon subsequently fails to encompass the ultimate singularity of collapse. The scenario above was derived by incorporating the physical characteristic that a realistic collapse necessitates an inhomogeneous density distribution. We must examine the emergence of a naked singularity during the gravitational collapse of a massive star, considering additional physical factors such as non-zero pressures, realistic equations of state, and non-sphericity. Specifically, will the naked singularity vanish when broader physical characteristics are considered? Consequently, dust is an idealization. Generally, the collapsing star will exhibit non-zero pressures. We can inquire whether gravitational collapse with non-zero pressures exclusively results in black holes, thereby eliminating the possibility of naked singularities. Moreover, a typical star does not require perfect spherical symmetry. It may also exhibit rotation. Will permitting deviations from sphericity prevent the occurrence of naked singularities? These inquiries relate to naked singularities' realism, generality, or stability, even if they emerge during collapse. It is essential to pose such inquiries and develop collapse models accordingly. If the inclusion of a specific physical characteristic during collapse consistently prevents the emergence of all observable singularities, this could provide a constructive approach to formulating and validating the censorship conjecture through physical, rather than solely mathematical methods. In recent years, researchers have investigated a broader array of scenarios and models of gravitational collapse that are more comprehensive and generic than the dust collapse model. We will examine several of those topics here. The fundamental conclusion from these studies is that the outcome of a star's collapse, resulting in either a black hole or a naked singularity, depends on its initial density and pressure profiles, velocity profiles, or the dynamical evolution of the collapsing matter shells. Naked singularities emerge during collapse, under relatively common initial conditions. Ultimately, we will inquire what causes the formation of a naked singularity during collapse. We seek to understand the physics underlying the formation of naked singularities. Specifically, the physical factors that lead to the emergence of a naked singularity instead of a black hole as a massive star undergoes its final collapse. This is where the captivating role and subtle complexities of general relativity arise. We will observe again how our Newtonian intuitions can falter, and how general relativity facilitates communication, even in regions of extreme density. The cosmic censorship conjecture, CCC, posits that the Oppenheimer-Snyder DAT, OSD model of uniform dust collapse applies to any physically feasible gravitational collapse of a massive star, introducing inhomogeneities in dust collapse, results in final states characterized by naked singularities. It is crucial to analyze the incorporation of additional physical attributes to assess their impact on the ultimate collapse states. In recent decades, numerous dynamical collapse scenarios involving clouds of dust, radiation, perfect fluids, and various matter compositions with generalized equations of state have been analyzed. To assess the legitimacy of censorship, we must examine the dynamic collapse of massive stars to ascertain their ultimate destiny. Recent analytical research on gravitational collapse has provided insights into the formation of black holes and the conditions under which they do not form. Certain models indicate that visible ultra-dense regions, or naked singularities, may emerge naturally and generically due to collapse. If so, the ramifications are substantial and affect nearly every facet of astrophysics and fundamental physics. They may elucidate exceptionally high-energy phenomena in the universe that remain inexplicable. They may also provide a laboratory for investigating quantum gravity effects that are otherwise exceedingly challenging to observe. Unlike the idealized and singular OSD model, actual stars display an inhomogeneous density at their cores, indicating that the internal pressure is not null. They also undergo rotation. Will every massive star that undergoes collapse after its life cycle transform into a black hole? Cosmic censorship posits that the singularity formed during collapse is invariably concealed within an event horizon, obstructing external observers from perceiving it. Regardless of the physical conditions and forces present within massive stars, their ultimate collapse must result in the formation of a black hole. Censorship restricts the permissible dynamical evolution of collapsing clouds in general relativity. From the perspectives of gravitational theory and astrophysics, the essential inquiry is whether we can genuinely observe the super-ultra-dense regions that form during the collapse of massive stars. True advancement in this field necessitates transcending mere hypothesis formulation and examining the gravitational collapse mechanisms of massive stars by applying the dynamical equations of gravitational theory. Significant efforts in recent years have yielded results, necessitating consideration of the potential implications if naked singularities arise from ongoing gravitational collapse. We must examine the possible theoretical and observable implications. The inquiry pertains to the possibility of generalizing the findings regarding dust collapse and the emergence of a space-time singularity during the collapse and black hole formation to encompass broader matter fields and non-spherical configurations. While the presence of a singularity is resilient to minor perturbations in the initial data, there is no indication that it will remain concealed within a black hole. When the collapse is non-spherical, or the matter is not uniformly distributed, it becomes causally isolated from external observers. Recent developments indicate that a collapsing star's ultimate outcome may be a naked singularity in numerous physically plausible collapse scenarios. A naked singularity resembles a black hole, albeit lacking its black aspect, as it constitutes an extraordinarily dense region of matter and space-time curvature in the universe that can interact with or be observed by distant entities. The formation of a naked singularity can occur during the final phase of a massive star's collapse, contingent upon the star's internal structure, including its density and pressure profiles, as well as the velocities of the collapsing shells. The ultimate destiny of the star is contingent upon the characteristics of the initial data from which the collapsing cloud develops, and the potential dynamical evolutions permitted by Einstein's equations of gravity. Black holes and naked singularities are theoretical astrophysical entities that represent a captivating fundamental physics and cosmology domain. The formation of naked singularities during the collapse of massive stars would significantly impact our observations of extreme high-energy phenomena in the universe and fundamental theories of nature. How can we address this significant theoretical and observational dilemma? And what potential future directions might emerge? What do contemporary astronomical observations suggest regarding the ultimate destiny of a massive collapsing star? What will these issues' implications and considerations for prospective quantum theories of gravity? Are there any potential model solutions that could assist us in solving this cosmic enigma? Overall, it is not an exaggeration to characterize these inquiries and the present circumstances as one of the most fundamental theoretical challenges arising from the theoretical and observational advancements in astronomy and astrophysics over the past decades. Given our focus on collapse, it is essential that the space-time features a regular initial space-like surface where the matter fields possess compact support, and that all physical quantities exhibit well-defined behavior on this surface. The matter must fulfill an appropriate energy condition, and Einstein's equations must be satisfied. Space-time is said to contain a naked singularity if a future-directed non-space-like curve extends to a distant observer or infinity in the future, terminating at the singularity in the past. To address the significant issue of cosmic censorship in gravitational physics, which lacks definitive evidence of its universal applicability, researchers, including our team, have examined various specific collapse scenarios that provide insights into the behavior of a massive star during its disintegration. We have performed a series of computational experiments to compile a list of conditions that result in gravitational collapse, leading to either a black hole or a naked singularity. Our strategy involved analyzing all potential evolutionary pathways for a massive star during its collapse, given a specific set of physically plausible properties and regularity conditions. These conditions are fundamental consistency requirements, ensuring the star retains positive energy throughout its gravitational collapse. These are the dynamical solutions permitted by Einstein's equations. We provide the foundational data for the collapse, including the initial density and pressure profiles of the stellar matter and the velocities of the collapsing concentric gas shells. Subsequently, we analyze the causal structure within the collapsing cloud, elucidating how gravity ensnares light and matter as the collapse escalates. This determines whether the ultimate singularity of collapse will be observable or obscured by a horizon. In recent years, we have established a comprehensive formalism for addressing spherical collapses utilizing standard initial data. General matter fields may encompass realistic characteristics such as pressure, density, distribution, inhomogeneities, and plausible equations of state for matter. Physicists are investigating scenarios in which matter converts into a fundamental quantum field, or experiences an abrupt phase transition into radiation during the final stages of collapse. These studies demonstrate that collapse under non-zero pressures can result in a black hole or a naked singularity. The initial conditions and dynamic developments, as permitted by Einstein's equations, determine the result. Collapse culminates in a naked singularity under various circumstances. The singularities examined thus far display a diverse array of fascinating structures. In certain models, the event horizon ultimately obscures the observable region. In other locations, they can persist in visibility indefinitely. This is contingent upon the type of collapsing matter, the equation of state, and additional characteristics. Singularities manifest in various forms, contingent upon the collapse model. The naked singularity typically originates at the geometric center of the collapse, but it may subsequently extend to other regions or obscure itself as the collapse progresses. The outcome of a naked singularity or a black hole is more contingent upon selecting initial data for the field equations than on the nature of matter or the equation of state, as will be elaborated upon later. These studies indicate that black holes and naked singularities emerge as the final stages of a realistic collapse, characterized by inhomogeneities and non-zero pressures within the collapsing matter cloud. The ultimate outcome of collapse, whether as a naked singularity or a black hole, is dictated by the initial parameters encompassing initial density, pressure, and velocity profiles of the collapsing shells, while adhering to specific regularity and energy conditions to guarantee the model's physical validity. This scenario has significant implications for cosmic censorship. To uphold the CCC, we must eschew any conventional initial data that may result in naked singularities. Consequently, a more profound comprehension of the initial data space is necessary to ascertain the specific initial data and the associated physical parameters they would delineate. This would delineate the spectrum of physical parameters to be eschewed for any selected form of matter, such as perfect fluids or dust, thereby permitting only black holes and excluding naked singularities. This will allow black hole physics to depend exclusively on the spectrum of allowable parameter values that produce black holes, reinforcing its foundation. This is where the true utility of gravitational collapse studies resides. Non-zero pressures are evidently significant during the later stages of a star's collapse. The ongoing gravitational collapse of a massive star at the astrophysical level transpires when the internal pressures from nuclear fusion diminish. As the collapse advances, pressures may become significant again and influence the subsequent phases. Consequently, the essential inquiry we must examine is how non-zero pressures can influence the collapse scenario, especially regarding the ultimate state of collapse. Researchers have determined that non-zero pressures do not produce qualitative differences in the outcome, as naked singularities and black holes emerge as end states of collapse. The sole distinction is that the initial data space for collapse is more extensive. The current data set encompasses density profiles, pressure profiles, and initial shell velocities, rendering it substantially larger than the previously examined dust collapse scenario. In the former scenario, solely the initial density dictates the ultimate state of collapse. Conversely, when examining collapse from a state of rest, a confluence of parameters influences the final state. The fundamental principle for collapse under non-zero pressures remains unchanged. The total mass within a specified radius governs the confinement of light in both scenarios. However, total mass has become a more complex function of the involved parameters. This formalism addresses the issue by fully integrating general pressures and illustrating the typical emergence of naked singularities and black holes, even in non-zero pressure. Initially, dust collapse models disregarded pressure. However, the general methodologies established to comprehend the dynamical evolution of collapse were subsequently applied when pressure-inclusive collapse models were examined. It is widely acknowledged that, under entirely general conditions, it is infeasible to globally resolve Einstein's system of equations, primarily due to their complexity as a set of non-linear partial differential equations. We can derive pertinent information regarding the final outcome of collapse in the general context of matter fields and curvature invariance by examining the behavior of solutions in proximity to the cloud's singularity and core. This enables us to determine the local visibility of the central singularity. In recent years, numerous groups have thoroughly examined and analyzed gravitational collapse models with non-zero pressures. Giulio Magli, Roberto Giambo, and their associates in Italy, along with Kenichi Nakao and others in Japan, investigated a form of pressure generated by the rotation of particles within a collapsing cloud. They demonstrated the formation of naked singularities as terminal states. We examined models featuring a realistic state equation that delineates the correlation between density and pressure within a cloud, including those proposed by Amos Ori, Zvi Piran, and our team. Kyle Lake and her colleagues investigated multiple collapse scenarios, obtaining comparable results, as did Tomohiro Harada. Even in the most straightforward scenarios, the inclusion of pressures hinders the complete integration of the system due to the complexities involved in solving Einstein's equations. The primary focus of our investigation and the principal methodology devised by our group to address this issue can be summarized as follows. Initially, we examined the overarching framework of Einstein's equations in the context of spherical collapse. Subsequently, we elucidate the procedure for integrating the equations to the first order, yielding the equation of motion for the system. We evaluate and enforce the regularity and energy conditions that result in physically plausible models. We subsequently examine the concluding phases of collapse, evaluating essential factors and ascertaining whether the outcome will be a black hole or a naked singularity. We illustrate a particular function related to the tangent of outgoing geodesics at the singularity, whose sign solely determines the formation time of trapped surfaces about the singularity. We investigate the emergence of trapped surfaces during collapse and the possibility for radial null geodesics to evade, thereby exposing the singularity. We can illustrate the correlation between both features and the sign of the function above, thereby establishing a necessary and sufficient condition for the visibility of the singularity. These widely accepted conclusions and models indicate that a physically plausible gravitational collapse can result in a naked singularity. In the initial formulation of the cosmic censorship conjecture, Roger Penrose stipulated a condition that generic gravitational collapse would invariably result in the formation of black holes. Are the models we have just examined generic? Indeed they are, as the preliminary data for the issue is entirely generic, as mandated. The primary challenge is the necessity for a mathematically rigorous definition of genericity in gravitational theory to fulfill this requirement. Explaining stability and genericity in general relativity is challenging due to the general nature of space-time and the indefinite signature of the Lorentzian metric, which results in the absence of clear and definitive criteria. Indeed, accomplishing this is laden with significant mathematical challenges. Consequently, the sole course of action poses additional inquiries, such as whether any perturbation of spherical symmetry could eradicate these naked singularities. Will naked singularities emerge from non-spherical collapse? In summary, the typical result of spherical collapse, with non-zero internal pressures within a collapsing star, is as follows. Gravitational collapse models, incorporating a general matter form, as well as those featuring directed radiation, dust, and perfect fluids, reveal a discernible pattern regarding the ultimate consequences of gravitational collapse. Consequently, the selection of initial data for the Einstein field equations dictates the emergence of a naked singularity. It will emerge from standard initial data within the overarching context, contingent upon fulfilling specific energy conditions. An equation of state is a constitutive relation that establishes a connection between essential quantities characterizing a system. Upon comprehending the correlation between pressure and energy density, we generally formulate an equation of state for a collapsing mass cloud. These equations of state can characterize stars in their equilibrium phase, and they are applicable in both classical mechanics and general relativity. Upon depleting its nuclear fuel, the star undergoes a rapid collapse from an initial state defined by identical physical parameters governed by the same equation of state. The pressures and densities can be considered initially derived from the models at equilibrium, which also applies to other quantities in the equation of state. We articulate all these values about the thermodynamic variables of the system, encompassing temperature and the molecular weight of the gas. We have examined instances of basic, astrophysically pertinent linear and polytropic equations of state and evaluated their collapse to ascertain their ultimate outcome as either a black hole or a naked singularity. This is beneficial for potential astrophysical and numerical applications. Researchers have examined the collapse of an ideal fluid characterized by isotropic pressures. The initial conditions completely determine the dynamics, illustrating that solving the equation of motion is tantamount to resolving the entire system of equations. As previously stated, introducing an equation of state completes the system of Einstein's equations, precluding the specification of further physical quantities. Ritupano Goswami and I investigated the gravitational collapse of a perfect fluid, characterized by a linear equation of state, to illustrate the existence of solutions that may result in either black holes or naked singularities, contingent upon the initial conditions and the distribution of particle velocities. An interesting observation is that as the collapse progresses, the equation of state may not remain constant. The equation of state may fluctuate, possibly even suddenly, during specific phase transitions or upon reaching the nuclear saturation limit of neutron star matter. Recent data indicates that intense negative forces may emerge just before the formation of the singularity, and the gravitational field may function to repel the infalling matter from the collapsing cloud. This effect can be inferred at a classical level. However, including quantum corrections makes it more apparent, as will be discussed. This evidence indicates that the equation of state connecting pressure and density, which must remain positive, undergoes complex changes during the collapse. A pronounced shift in equations of state may occur when matter transitions between distinct physical regimes. Under intense negative pressures, the speed of sound within the matter cloud may approximate the speed of light. It is imperative to enhance our comprehension of the equations of state governing ultra-compact objects, as these phenomena necessitate more complex formulations than the conventional linear and polytropic equations of state to adequately address such extreme conditions. Subsequently, we may either eliminate the equation of state entirely or investigate more unconventional equations of state. Gases with unusual properties, such as Chaplygin gas, have been examined as potential sources of dark energy and matter. While dark energy effects are unlikely to influence collapse at stellar scales, they may become significant for larger entities, such as the compact objects residing at the centers of galaxies, which possess masses in the range of several million solar masses. In light of the collapse under non-zero pressures, we naturally question the significance of the cosmological term that Einstein incorporated into his field equations. This term is presented as an ancillary term and is often regarded as negligible. Recent evidence concerning dark energy and the observed acceleration of the universe has significantly revived the possibility that we inhabit a universe with a non-zero cosmological constant. The cosmological term acts as a vacuum energy density, with its positive or negative sign influencing positive or negative pressure. Researchers, including ourselves, have also examined gravitational collapse with a non-zero cosmological constant. The findings indicate that during the collapse of a compact object, such as a massive star, the matter densities are generally significantly greater than the vacuum energy density. Consequently, the collapse end states of a black hole and a naked singularity remain unchanged. Nonetheless, in the case of an extensive cloud with minimal initial densities, the cosmological constant may exert influence, and when positive, it could occasionally initiate the cloud's rebound. Although we comprehensively understand spherical collapse for a generic matter field with pressures, non-spherical collapse still needs to be explored. Numerous recent studies have identified non-spherical models that result in naked singularities. We must ascertain whether these circumstances are contrived. Rapidly advancing numerical core collapse models in general relativity may provide assistance in this context. What will be the final result of a non-spherically symmetric gravitational collapse? The primary phases in the spherical collapse of a massive star typically include instability, the implosion of matter, the formation of an event horizon alongside a space-time singularity characterized by infinite gravity and curvature. As previously mentioned, the horizon may not encompass this singularity. Minor perturbations in a spherically symmetric scenario will not alter its state, as an event horizon will persist and form during the later phases of the collapse. Can horizons still form when fluctuations from spherical symmetry are significant, and the collapse is markedly non-spherical? Kip Thorne established 1972 that the collapse of infinite cylinders, lacking spherical symmetry, results in naked singularities in general relativity, which are not obscured by event horizons. Thorne proposed the subsequent hoop conjecture for finite systems within an asymptotically flat spacetime, elucidating the phenomena occurring after a multiverse collapse. Gravitational horizons emerge if and only if a mass, m, is concentrated within a region where the circumference, c, in all directions satisfies c. 2p, 2gmc2, with g representing Newton's gravitational constant, and c denoting the speed of light. Consequently, in contrast to the cosmic censorship conjecture, the hoop conjecture does not preclude all naked singularities, but makes a specific assertion regarding the formation of event horizons during gravitational collapse. The hoop conjecture pertains to creating event horizons rather than naked singularities. Consequently, the formation of event horizons, such as in the spherically symmetric scenario, does not preclude the existence of naked singularities. It does not suggest that such horizons must invariably encompass the singularities. Non-spherical collapse is typically intricate, necessitating numerical analysis of the collapse evolutions. Nonetheless, we observe that, in addition to numerical simulations, certain analytical approaches to non-spherical collapse are also accessible. Andrei Krolak and I investigated the non-spherical Szekeres models for irrotational dust, which are devoid of symmetries, and generalize the spherical Lemaitre-Tolman-Bondi collapse, to establish the presence of strong curvature central naked singularities. Killing vectors for spacetime typically delineate the symmetries of a specific model. The Szekeres models lack killing vectors, rendering them fascinating non-spherical models. Thus, this significant result indicates that spherical symmetry does not invariably constrain naked singularities. We have conducted a thorough analysis of these models. Nonetheless, we must recognize that the dynamic progression of a non-spherical collapse is predominantly unexamined. We must employ numerical models of collapse within the framework of full general relativity to gain insights into the ultimate outcome of the collapse in such a comprehensive context. Conversely, we can predominantly conduct analytical work in the spherical scenario, which provides enhanced transparency. We utilize analytical methods to solve Einstein's equations in the spherical context, creating a thorough framework for diverse physical matter fields, including dust, perfect fluids, and radiation collapse. We can solve Einstein's equations to partially ascertain the structure of trapped surface geometry and the apparent horizon as the collapse progresses. This enables us to explicitly ascertain the presence of families of null geodesics and in certain instances, other time-like curves originating from the singularity, along with the physical conditions that govern their existence. The photon trajectories that intersect the singularity in the past and progress towards the future encounter external observers in space-time, thus making the singularity or the super-ultra-dense regions nearby observable. This demonstrates that the singularity is observable rather than obscured by an event horizon. We clearly delineate the conditions under which the collapse end state results in a naked singularity versus a black hole, considering the initial parameters, including the density and velocity profiles of the collapsing matter, and the permissible evolutions of Einstein's equations. We analytically determine the geometry of trapped surfaces, and due to their inherent nature and methodology, the conclusions are independent of coordinates. Nonetheless, this formalism's constraint is its predominant applicability to spherical collapse, despite its relevance to entirely generic matter fields. Moreover, the geometry of the trapped surface suggests that it will maintain stability despite minor perturbations in space-time. Most of the collapse models examined to date are spherical. Roy Kerr indicated to me in a private discussion that numerous physicists contend that for cosmic censorship to be a fundamental principle of nature, it must also be applicable within the spherical category, which possesses considerable astrophysical relevance. Examining these models may provide significant insights regarding censorship. This will assist in isolating the physical characteristics that induce naked singularities. Conversely, certain researchers contend that the collapse classes examined to date are sufficient for exploring naked singularities physics and astrophysical ramifications. The main question at present is whether these circumstances are contrived. Rapidly advancing numerical core collapse models within the general relativity framework may assist in this context. The results thus far indicate that naked singularities are indeed stable against minor perturbations in the initial conditions of matter fields, the introduction of non-zero pressures in the surrounding cloud, and similar factors. Consequently, we have not yet identified and accurately isolated the perturbation that would cause a specific naked singularity to vanish. Physicists characterize these scenarios as generic, indicating they are devoid of artifice, as even minor alterations in the initial data produce fundamentally identical results. Nonetheless, it is crucial to emphasize that the general stability proof for the naked singularity remains unresolved. The stability and genericity of naked singularities are intrinsically linked to the final outcome of a non-spherical collapse. In the context of non-spherical collapse, examining the deformations that indicate a deviation from spherical symmetry is essential. This constitutes a significant unsolved analytical problem, as the set of Einstein's equations governing the cloud's evolution becomes exceedingly complex when accounting for deformations and rotation. Attempts have been made to investigate quasi-spherical and cylindrical collapse in comprehensive detail. However, the physical implications of these models still need to be clarified. Significant research is still required to investigate non-spherical collapse within the precise solutions of Einstein's field equations. Numerical relativity offers insights into the final outcome of a non-spherical cloud's collapse, as a complete analytical solution for collapse deviating from spherical symmetry is not feasible. The no-hair theorem posits that only three quantities, mass, charge, and angular momentum, characterize any asymptotically flat black hole vacuum solution of Einstein's equations, thereby connecting the investigation of non-spherical collapse to cosmic censorship. Vacuum solutions exhibiting varying characteristics, such as elevated multipole moments in axially symmetric spacetimes, may also possess a naked singularity. This pertains to the category of metrics known as Weil metrics. Consequently, a significant concern regarding non-spherical collapse is the behavior of higher multipole moments during the collapse phase. Schwarzschild, or Kerr. Geometries will not depict the ultimate vacuum configuration if the collapsing cloud retains its non-spherical form. Naked singularities may exist in axially symmetric vacuum spacetimes, such as the Weyl class or the Tomimatsu-Sato solution. Conversely, deformations may modify the density distribution of the collapsing source, counteracting gravitational attraction. This suggests that non-spherical sources may establish an equilibrium state before total collapse, resulting in a singularity. Recent investigations have analyzed the observational signatures of vacuum metrics, indicating that the Kerr metric may not be the most appropriate for characterizing the exterior of a rotating star. In contrast, if we emit higher-order multipole moments during the collapse, we attain Schwarzschild or Kerr-Newman spacetime as the ultimate configuration. For this to transpire, a mechanism within Einstein's equations must elucidate the reasons and methods by which the higher multipole moments dissipate, a mechanism that remains conjectural. Furthermore, the potential for event-like naked singularities to emerge during the collapse of spherical symmetry persists. Examining minor perturbations in spherical symmetry indicates that the resultant states, whether black holes or naked singularities, are predominantly stable. Both analytical and numerical approaches have examined gravitational collapse. Numerous inquiries regarding total collapse still need to be solved from theoretical and observational standpoints, including the mechanisms underlying supernova explosions and the origins of gamma-ray bursts. Computer simulations may be highly beneficial in addressing these inquiries. We will examine certain findings and outstanding issues here. Given the difficulties in resolving Einstein's equations in complex scenarios, such as non-spherical collapse with rotation, numerical simulations can provide significant insights into unattainable issues via analytical approaches. The most critical factors pertain to ascertaining the final result of a substantial cloud's total collapse and the fusion of two dense entities. Both cosmic censorship and astrophysics pertain to these phenomena. Numerical simulations allow for examining effects that, although overlooked in analytical approaches, are of considerable significance in astrophysics. Consequently, we can utilize them to investigate the mechanisms underlying supernova explosions, core collapse, and high-energy phenomena associated with stellar demise. The numerical modeling of gravitational wave production, the paramount objective of contemporary gravitational physics, is essential for successful experiments such as LIGO and Virgo. Currently, only numerical simulations enable the examination of the essential components of electromagnetic fields and accretion disks that affect the implosion process of a star's core. These are the sole methodologies available to elucidate the occurrence of high-energy observed phenomena, such as relativistic jets or gamma-ray bursts. The total collapse of a substantial cloud results in a singularity, which may be obscured or observable, contingent upon the initial conditions. A critical concern in these simulations is the management or removal of singularities, as numerical methods cannot address diverging quantities. A numerical model that eliminates the singularity region from the simulation may provide a minimal understanding of cosmic censorship, irrespective of an observable horizon. Nonetheless, comprehending the rotation and dissipation of higher multipole moments, which may determine the transition to a Kerr black hole or an axially symmetric naked singularity, remains highly beneficial. Numerical models, conversely, can delineate the apparent horizon in more intricate matter configurations, offering insight into the destiny of trapped surfaces in authentic collapse scenarios. We have examined two primary collapse scenarios pertinent from an astrophysical perspective. These pertain to the total collapse of rotating bodies and the coalescence of two compact objects. It is crucial to recognize that incorporating sufficient elements to enhance the realism of the simulation significantly increases computation time, necessitating the utilization of highly advanced computers. Simulations frequently necessitate the limitation of the parameter space under consideration. Historically, researchers have performed simulations in one or two spatial dimensions. However, only recently have comprehensive 3D simulations of core collapse supernovae and binary mergers facilitated a more thorough examination of these phenomena. Consequently, due to the reason above, simulations that account for the microscopic structure of matter, including neutrino emissions and electroweak interactions, generally classify as non-relativistic. Conversely, fully general relativistic simulations frequently neglect the microscopic intricacies of the matter cloud. Luciano Rezzolla, Leus Lehner, and colleagues examined the principal characteristics of the total collapse of a rotating body via numerical simulations, focusing on the effects of rotation and magnetic fields. These influence the terminal phases of collapse and determine the waveform of gravitational waves and the configuration of the accretion disk encircling the ultimate compact object. We can elucidate essential inquiries regarding cosmic censorship by analyzing the expulsion of outer layers from the collapsing rotating entity. This encompasses the inquiry of whether the collapse of a rotating body invariably results in a Kerr spacetime, or if a rapidly rotating object can collapse into a superspinning Kerr solution. Furthermore, these simulations yield significant insights into astrophysical inquiries, including the mechanisms by which rotation-induced matter, expelled during collapse, reaccumulates around the compact object as an accretion disk. The attributes of these accretion disks regarding thickness, angular momentum, and luminosity, and the effects of a magnetic field on particle infall and the generation of high-energy jets. Another fascinating phenomenon is the coalescence of binary neutron stars, or black holes. The models illustrate the coalescence of two inspiraling compact entities: black holes, neutron stars, or a combination of one black hole and one neutron star. We have examined the impact of disparate masses on the final configurations of objects and proposed multiple scenarios in which the system evolves into a final Kerr black hole, accompanied by an accretion disk. Such mergers may occasionally transpire in the universe and constitute a significant source of gravitational waves. A primary outcome of these simulations is the merger waveform simulation. A potential mechanism for generating gamma-ray bursts is accretion disks, which describe how matter from the disk accumulates onto the final compact object. Investigating the potential emergence of superspinning Kerr spacetimes is essential to the cosmic censorship conjecture. This type of spacetime can generate compact objects that rapidly rotate, leading to collisions where particles from the accretion disk augment angular momentum, or when a star with significant angular momentum disintegrates entirely. There are no conclusive findings regarding the potential formation of superspinning Kerr spacetimes. However, existing spacetimes indicate that overspinning a Kerr black hole may be unfeasible. The discourse on these matters remains highly open-ended. The mechanism for generating this final configuration markedly differs from that of producing a Kerr black hole. We have advanced toward a feasible characterization of the mechanisms resulting in Type II supernova explosions. We have conducted various configurations of numerical simulations, accounting for microscopic effects, to develop a feasible model for generating the shock waves associated with the formation of these supernovae. These simulations depict the core collapse of a star from a microscopic perspective, considering nuclear interactions and neutrino generation. In recent years, this domain has achieved considerable advancements, as computational capabilities have become adequate for comprehensive 3D simulations, emphasizing the impact of neutrino generation during the explosion. Nonetheless, these simulations face a challenge. Despite incorporating neutrino heating, the explosion's efficacy remains inadequate to initiate a supernova. In the simulations, the explosion dissipates after several hundred kilometers. Nearly all models of Type II supernova, explosions, produce a shock wave when infalling matter from the outer layers encounters the inner compact core. The compact object at the center is a barrier against which matter from the outer layers rebounds, generating the shock wave. The dimensions of the core producing the shock wave dictate its energy. Nonetheless, in the event of a total collapse, it remains plausible that an alternative boundary, a quantum gravity limit, exists at a reduced scale. This is the point at which general relativity fails, forecasting a singularity. Upon reaching this threshold, an additional shock wave may arise. Consequently, if the collapsed structure lacks a horizon at that moment, a shock wave may radiate outward, supplying the requisite energy for the explosion to transpire. We have yet to perform simulations to evaluate these potential effects, leaving us uncertain about their viability as a solution to the problem of missing energy in Type II supernova explosions. Numerical investigations of the collapse of a rotating gas cloud suggest that a final state with excessive angular momentum is improbable to occur under typical conditions. Consequently, a Kerr black hole seems to be the most probable ultimate result. Physicists are investigating the observational characteristics of singular spacetimes to comprehend the potential traces and effects that overspinning naked singularities might impart on the universe if allowed. We lack evidence that such configurations will emerge from the collapse of a cloud with standard initial data. Similarly, we have no proof that such configurations are prohibited. Stuart Shapiro and Saul Tucholsky's compelling research has demonstrated that axially symmetric collapse can result in the emergence of naked singularities. This is useful when addressing the non-spherical scenarios of oblate and prolate collapse. They analyzed the collapse of collisionless particles and simulated it numerically. They found that in a specific slicing, no trapped surfaces emerged as one approached the singularity, prompting the inquiry of whether the singularity was naked. This provides compelling numerical data regarding the potential ultimate outcome of non-spherical dust collapse, suggesting the possibility of a naked singularity. Additional information on non-spherical collapse is essential, and this represents a significant advancement in that direction. Matthew Choptwick noted another fascinating phenomenon in the numerical analysis of the spherical collapse of a massless scalar field: the critical behavior. This study addresses a specific category of scalar field collapse models, analyzed numerically. Fluctuations in the family's parameters define the emergence of small black holes, a naked singularity, and the ensuing dispersion of the field, all demonstrating fascinating numerical characteristics. Object-like singularities indeed emerge from gravitational collapse. Homogeneous dust collapse results in the formation of the Schwarzschild singularity in a black hole. Nonetheless, no precise analytical model exists within Einstein's theory to generate a Kerr singularity or Kerr black hole through collapse. Is it possible to derive an object-like, long-lived naked singularity from gravitational collapse? The response is affirmative. Gravitational collapse forecasts ephemeral event-like naked singularities in numerous models. However, it may also yield enduring object-like naked singularities in certain instances, as Daniele Malafarina, Ramesh Narayan, and I demonstrated recently. We demonstrated that general relativity anticipates equilibrium configurations of ordinary matter supported by non-zero pressures. These objects may be an alternative to astrophysical black hole candidates, including the galactic center. The previously mentioned type of long-lived singularity offers fascinating prospects within the category. These are interior solutions that characterize a uniform source with a distinct center. This ultimate state contrasts with vacuum solutions, such as the Kerr metric. This pertains to a finite matter cloud with a boundary exceeding the horizon and a singularity at its core. Interior solutions of Einstein's field equations have been regarded for decades as sources of the gravitational field. Constructing such interiors necessitated a consistent matter density at the source center. However, there is no justification for imposing that a stable configuration cannot develop with a singularity at its center. These singularities represent the area of infinitely high density that forms at the object's core, where gravitational forces display extreme characteristics. Consequently, it is plausible that such a source exhibits observational differences compared to a corresponding entity with a conventional interior or a vacuum solution, such as a black hole. If the cloud's overall density is sufficiently low, as observed in supermassive objects at the centers of galaxies, then phenomena occurring near the center, such as particle collisions and lensing, may be observable to distant observers. Concerning gravitational collapse, smaller, explosive, and ephemeral phenomena exist, exemplified by the collapse of a star's core. These generally entail exceedingly high energies and constrained timescales. Conversely, identifying active galactic nuclei has prompted astronomers to hypothesize that supermassive black holes exist at the core of galaxies. Further comprehension of these objects is necessary, and it is highly probable that processes such as gravitational collapse, occurring on a significantly larger scale and over extended timescales, are essential to their evolution. We proposed a category of solutions for Einstein's equations that exhibit naked singularities. These solutions emerge asymptotically for appropriate matter models, when the opposing pressures effectively cease the process. This collapse process results in an equilibrium configuration as the final state. These models illustrate the evolution of a typical matter cloud as it transitions over time to achieve equilibrium, possessing a radius exceeding the Schwarzschild radius and an empty region at its center. The process may require significant time to attain the equilibrium configuration, and the cloud's average density at the final equilibrium may remain low. This indicates that such a model can elucidate the formation of supermassive entities, aside from black holes, that may inhabit the cores of galaxies. If it existed, such an object would possess distinct properties in its surrounding accretion disk compared to that of a black hole, thereby rendering it, in principle, observationally distinguishable. After acquiring the equilibrium object models, featuring a singularity at the center, we juxtaposed their observational characteristics with those of a black hole of equivalent mass. We specifically examined the accretion disks in both instances. A standard thin accretion disk can only exist at radii with stable circular orbits. Consequently, for a Schwarzschild black hole, the inner edge of an accretion disk will be located at a finite distance from the center and beyond its event horizon. Within this radius, the accreting gas descends or free falls. However, this does not apply to a naked singularity object, where the accretion disk closely approaches the singularity. This scenario suggests multiple intriguing implications. We demonstrated that a perfect, fluid cloud, gradually evolving and collapsing under gravitational influence, can ultimately achieve a static, spherically symmetric equilibrium state, with an arbitrarily high central density devoid of an event horizon. Subsequently, we examined a specific configuration with a finite outer radius and developed a toy model. We examined the observational characteristics of a thermal accretion disk in this spacetime and compared them with those anticipated for a disk surrounding a black hole of equivalent mass. Several significant and compelling distinctions arise. A disk surrounding a naked singularity exhibits significantly greater luminosity than one encircling a comparable black hole. An accretion disk surrounding a naked singularity exhibits a spectrum characterized by a high-frequency power law segment that accounts for a significant portion of the total luminosity. This analysis results in the observational differentiation of certain naked singularities from black holes of equivalent mass. If this scenario is broadly applicable, it would yield several valuable and fascinating implications. These naked singularity models are readily distinguishable from black holes of equivalent mass. Consequently, employing observational data on astrophysical black hole candidates may prove advantageous and compelling in assessing the permissibility and viability of a comparable naked singularity. It's reasonable to inquire how a signal can elude super and ultra-strong gravitational fields, and why any observable singularity should emerge during gravitational collapse. The fundamental inquiry is, what causes the formation of a naked singularity? To address this inquiry, we will examine various collapse scenarios and their distinct characteristics. Dust collapse. The ultimate outcome of the collapse, contingent upon the selected velocity profiles for the collapsing shells, can result in either a black hole or a naked singularity, given any standard density profile or mass function for the cloud. A uniform density typically results in the creation of a black hole. A greater inhomogeneous density at the center, a more physically plausible scenario, leads to a naked singularity. We determine that adequate inhomogeneity leads to the formation of a naked singularity. Perfect fluids. We have achieved various numerical and analytical results and examined multiple collapse models. We observe the emergence of black holes and naked singularities as collapse results. From the cosmic censorship conjecture perspective, it is significant that the introduction of pressures does not qualitatively alter the outcome of the collapse, similar to the scenario of dust collapse. Spherical collapse characterized by non-zero tangential pressure and negligible radial pressure. This category of collapse models, referred to as Einstein cluster models, facilitates a completely analytic and clear collapse treatment. Numerous models offer significant analytical insights into the outcomes of gravitational collapse, indicating that both black holes and naked singularities can serve as final states. General matter fields. Researchers have examined the collapse of fully general matter fields, adhering to positive energy conditions, regularity of initial data, and both non-zero radial and tangential pressures. With specified initial data for density and pressure profiles, Einstein's equations dictate extensive evolutions that result in either a black hole or a naked singularity, contingent upon the selection of initial data and the subsequent evolutions. Vidya radiation, collapse, models. This particular category of collapse models has yielded significant understanding regarding the ultimate outcome of collapse, specifically about black holes or naked singularities. We examine the failure of radiation shells utilizing the Vidya class of space-time geometries, ensuring that the analytical approach is lucid and comprehensible. Consequently, we can observe the causal structure adjacent to the singularity and comprehend how the horizons circumvent the singularity to render it invisible. The rate of collapse, or the velocity of matter accretion at the center, dictates the formation of either a black hole or a naked singularity. We have meticulously examined the numerical and analytical approaches to the gravitational collapse of massless scalar fields, focusing specifically on models that exhibit self-similarity, a form of scale invariance. We have identified several fascinating characteristics, including the formation of minuscule mass black holes, critical behavior, and naked singularities. According to the chosen definition of genericity, these models assert that forming a naked singularity is non-generic. Scholars have also investigated scalar fields with a non-zero potential. Researchers have once more observed the emergence of a perpetually visible singularity. The cloud can emit all its mass energy as the collapse progresses. Non-spherical collapse. Our examination of this scenario has been limited to several somewhat atypical models. While we have acquired some understanding of the formation of black holes and naked singularities, this area remains largely unexamined. Stuart Shapiro and Saul Tucholsky analyzed numerically computed oblate and prolate collapse models. They determined that no trapped surfaces exist in a particular slice as one approaches the singularity. This observation strongly indicates the potential for universal behavior in non-spherical collapse. Collapse with a non-zero cosmological constant. A non-zero cosmological constant in Einstein's equations may influence the ultimate outcome of collapse, as examined by researchers. Based on its sign, the cosmological constant applies either negative or positive pressures. The final states of collapsing compact objects, such as stars, remain consistent as either black holes or naked singularities. Nonetheless, for substantial matter clouds with minimal initial densities, a positive cosmological constant associated with a negative pressure effect can initiate a cloud bounce, thereby circumventing the singularity. Collapse in higher dimensional spacetimes. Scholarly investigations have explored various collapse models within higher dimensional spacetime geometries, in a classical context, to examine the potential for reinstating cosmic censorship in elevated dimensions. Nevertheless, the primary results of the conventional 4 dimensions remain qualitatively unchanged. This method seems to be ineffective in reinstating the censorship hypothesis. The issue of whether alternative theories of gravity, such as higher derivative theories, can avert naked singularities remains unresolved. Researchers have investigated alternatives such as Lovelock gravity and incorporated the Gauss-Bonnet term. The results once again corroborate Einstein's theory's conclusions. This list enumerates the physical scenarios of gravitational collapse that have been examined and analyzed. The main issue has been whether these scenarios result in the creation of an event horizon. The cumulative efforts over these decades elucidate the outcomes of gravitational collapse, as described by Einstein's theory of gravity, offering insights into the formation of either a black hole or a naked singularity resulting from such collapse. The overarching framework for spherical collapse, previously examined, encompasses numerous aforementioned scenarios to forecast collapse results. It is reasonable to inquire about the physical mechanisms that lead to forming a naked singularity instead of a black hole. The compelling inquiry is why powerful gravitational fields permit the escape of all particles and energy. We have analyzed this issue to emphasize the influence of inhomogeneities and shearing effects on forming horizons during the collapse in spacetime and spacetime geometry. In Newtonian gravity, the gravitational field is solely determined by matter density. In Einstein's theory, density is merely one characteristic, while various curvature and scalar quantities are equally significant in determining the overall nature of the field. Our findings indicate that the core of a collapsing star delays the entrapment of light and matter during the collapse, permitting their escape. Inhomogeneously collapsing matter fields generate trajectories for light or matter to evade, even under extreme densities, and these physical characteristics inherently facilitate the emergence of a naked singularity. Consequently, the degree of inhomogeneity contributes to the distortion of the horizons. If the degree of inhomogeneity is minimal, it will result in a black hole below a critical threshold. Conversely, if it is substantial, it postpones trapping and produces a naked singularity. The significance of this issue is evident in the Vidya class of radiation collapse models, where the rate of cloud collapse dictates the emergence of a black hole or a naked singularity. If a matter cloud with zero internal pressure exhibits a pronounced density gradient, the formation of an event horizon will be contingent upon the relatively dense inner regions of the star. However, these regions may, due to basic geometric considerations, be deficient in the necessary total mass. In instances of inhomogeneous collapse, if the density decreases sufficiently quickly from the star's center at any moment, there will never be an adequate mass within a specified radius to induce complete light trapping. This procedure enhances the visibility of the singularity. This occurs in a physically realistic scenario when a star's initial density decreases from the center at an appropriate rate rather than remaining constant. Suppose the density difference between the center and a small radius increases proportionally to either the first power of the radius or its square. In that case, there will never be sufficient mass within a specified radius to capture light, resulting in a final state of collapse that is invariably a naked singularity. Nonetheless, the collapse creates a black hole when the alteration is sufficiently gradual or ceases, a phenomenon referred to as the homogeneous case. Consequently, adequate inhomogeneity in density distribution within a collapsing star results in a naked singularity. In other instances, the critical concern may be the timescale of collapse. The rate of cloud collapse in radiation collapse models influences light trapping. As the collapse intensifies, the mass concentration in a particular area is inadequate to capture light. Various physical factors can impede or obstruct light trapping in stars with diverse forms of matter, equations of state, and initial density and pressure profiles, thus allowing for the visibility of the singularity. The primary focus is the physically realistic characteristics of the gravitational collapse models under consideration. Researchers have meticulously verified that all physical regularity conditions, including the energy condition and the regularity of the initial data, are adequately maintained. We consider the work trivial if those precautions were not implemented. The guarantee of physical plausibility has rendered recent research on gravitational collapse intriguing and deserving of scrutiny, igniting a global discourse on the essential questions regarding the ultimate fate of gravitational collapse and the related concept of cosmic censorship. We seek to clarify the general relativistic effects, as opposed to Newtonian ones, that determine whether a singularity possesses clothing. We aim to elucidate the reasons for the emergence of naked singularities and identify the underlying physical factors involved. We need a more profound comprehension of the physical processes and principles involved in forming naked singularities. During the collapse of an inhomogeneous star, the entrapment of light does not occur swiftly enough to establish the event horizon before the formation of the singularity. In that scenario, at least a portion of the singularity becomes discernible. The critical matter of collapse, timescales, is likely connected to this, necessitating further investigation for a more profound comprehension. The inhomogeneities solely induce the space-time shear, a fundamental relativistic effect observed in the specific examples we examined for dust. These shearing effects distort the geometry of space-time and space-time surfaces, permitting light rays to escape. In such instances, permitting inhomogeneity in density or pressure significantly modifies the configuration of an apparent horizon. Deviating from the homogeneous collapse scenario we examined here leads to a postponement in light trapping. Recent collapse studies indicate a paradigm shift in our comprehension of the ultimate fate of a massive star's gravitational collapse, in contrast to stellar life cycles. Middle-mass stars may evolve into neutron stars following their initial collapse and a supernova explosion, whereas high-mass stars can transform into a black hole or a naked singularity due to continuous collapse, contingent upon their internal structure. The preceding sections indicate that when a massive star undergoes collapse after its life cycle, the general theory of relativity predicts the formation of either a black hole or a naked singularity contingent upon the star's internal structure. These are two separate entities or phenomena in the universe, and their observable characteristics should vary considerably. The black hole is defined by an event horizon, a unidirectional boundary through which matter and light can enter but cannot exit. Conversely, a naked singularity is an exceedingly dense observable region of the universe, where densities, curvatures, and all other physical quantities reach extreme values. Quantum gravity effects are expected to significantly influence the physics near the singularity, impacting observations in that region. The primary assertion is that the outcomes of gravitational collapse, specifically black holes and naked singularities, exhibit significantly distinct observational signatures, enabling the determination of whether the realistic collapse of a massive star results in one or the other. Recent advancements in comprehending the properties of accretion disks for black holes and naked singularities may elucidate observable distinctions between these phenomena. We will address several of these aspects subsequently. Furthermore, when a naked singularity occurs, minor inhomogeneities in matter, densities near the singularity epoch, can proliferate and amplify significantly, resulting in highly energetic shock waves. This may be linked to exceptionally high-energy astrophysical phenomena in the universe, such as cosmic gamma-ray bursts, which remain incompletely understood. Although exploring these possibilities is limited, general relativity's prediction of black holes and singularities as viable collapse outcomes offers ample motivation for further inquiry. Moreover, as previously stated, insights for developing a quantum theory of gravity, a comprehensive theory of natural forces, may potentially arise from observing ultra-high density regions in the universe, particularly if the collapse of a massive star leads to a naked singularity. The essential inquiry is whether we will witness a cosmic spectacle of collapsing stars in the celestial arena when a visible singularity emerges. Will the black hole curtain obscure it indefinitely, even before the cosmic performance can scarcely commence? Only forthcoming observations of massive collapsing stars in the universe will provide clarity.